Okay, now let's take a look on few examples here. We will discuss about this transient response in these few examples. So the first example, let's consider a unity feedback system where the open loop transfer function looks like this. And then we are going to evaluate the unit step response. Okay, how to do that? Remember again, what we have here is a unity feedback system. So what does it mean? You still remember what unity feedback system is? Unity feedback system is a system that looks like this, right? But the feedback part is just like this. But it is known that the open loop transfer function is equal to GS. So the open loop transfer function is 1 over S plus 1. So this is the system that we are talking about. And to this system, because we are going to consider a unit step response, to this system, a unit step input is given. So the input to this system is unit step. Unit step in Laplace domain is 1 over S, right? So how to do that? Let's evaluate the equivalent transfer function of this system. You still remember how to evaluate this unity feedback system? The transfer function of this unity feedback system will be equal to the open loop transfer function divided by 1 plus open loop transfer function. This is the open loop transfer function. So it's equal to GS divided by 1 plus GS. Right? So this is the GS. GS is known, 1 over S plus 1. So if once you substitute it to this equation, the equivalent system of our unity feedback system will be like this. You can check it by yourself. So if we look at this transfer function, it is clearly seen that this is a second order system, right? Why? Because if you look at the denominator, the highest order is 2. And let's refer to the generic form of a second order system. The generic form of a second order system is like this, right? S square plus 2 zeta omega ns plus omega n square, correct? Okay, so from the previous analysis, we can conclude that the omega n is equal to 1 and the zeta is 0.5. We only need these two parameters, zeta and omega n, to identify the features of the step response. Okay. Using the formula that we have already discussed before, you can find the sigma, where sigma is equal to zeta omega n. You can find the omega d, right, which is equal to omega n square root of 1 minus zeta square. And from there, you can use all of the formulas of the settling time, peak time, rise time, and maximum overshoot. So use all of the formulas using all of these values, and from there you can identify all of the features. The rise time, you can find it will be equal to 2.42 seconds, the peak time will be 3.63 seconds, and the maximum overshoot is 16.3%. Okay. Once you have all of these features, you can sketch the response. Okay, and then the settling time, we can also calculate it using the formula. So the settling time will be 8 seconds. Using all of this, the rise time, peak time, maximum overshoot, and settling time, you should be able to sketch the unit step response there. So this is the one that you can see on the right side is the sketch unit step response. This agrees with what we just calculated. The rise time will be around 2.42 2.4 here, 2.42 from our calculation. The peak time will be around, I don't know, 3.63 in our calculation. Okay, this will be the maximum overshoot, as what we have calculated before. The maximum overshoot will be 16.3%, and the settling time with a 2% criterion. So 2% criterion means the window will be between 1, because the steady state value is 1, so the window will be within 1.02 and 0.98, and from our calculation the settling time will be 8 seconds. So the window, probably, if I have to draw it correctly, the window might be something like this. Okay, so that's how you sketch the step response based on the parameters of your second order systems, zeta and omega n, and then from there you can calculate the features using the formula. So from there you can sketch the step response. Let's take a look on the second example here. So what you see here is a non-unity feedback system, right? Just to refresh your memory again, why do I call it non-unity? Because you have a transfer function on the feedback part. If you have this case, let's call this as GS, and if I call this HS, so you still remember on how to analyze a feedback system. The closed loop transfer function, the equivalent of this system, will be a system where the transfer function is equal to the forward loop transfer function divided by 1 plus open loop transfer function, right? So your GS is 16 over S plus 0.8, and the HS is 1 plus KS. Using this formula for the non-unity feedback system, after you substitute all of these GS and HS, you can check it again by yourself for exercise. The transfer function of this non-unity feedback system will be like this. Okay, but in here there is one unknown parameters. The parameters is this lowercase k. Now there is the unknown parameters. In this example, we are asked to determine the value of k, of this lowercase k. In such, our system here, our non-unity feedback system, will behave like an underdamped second order system with a damping ratio with zeta equal to 0.5. So what do you have to do? Let's refer again to the generic expression of a second order system. So if you still remember again, the generic expression of a second order transfer function is like this: 2 zeta omega ns plus omega n square. So in our non-unity feedback system now, the omega n square is 16, so our omega n is 4, definitely. The k, the DC gain, is equal to 1, obviously in our case here. And then now the 2 zeta omega n is 0.8 plus 16k, the lowercase k. From here we know that the omega n is 4 radian per second. Now we are going to determine the value of k in such the damping ratio zeta is equal to 0.5. So how to do that? We just have to make sure that this part is equal to this part. So 0.8 plus 16k should be equal to 2 zeta, the desired zeta, 0.5 times omega n. Omega n we have already calculated before. So This value 0.8 plus 16k should be equal to 4. From there you can identify the desired lowercase k here. By evaluating that equation, you can find that k should be equal to 0.2. Okay. Similarly, you can also calculate the remaining parameters, the remaining values, like omega d, the damn natural frequency, where you know that omega d is equal to omega n times square root of 1 minus zeta square. You can find that omega d is equal to 3.46. Beta basically is the angle of your damping ratio. We know that damping ratio is equal to cosine of beta, so you can find beta, as well as sigma. You know that sigma is the real part of the pulse, which is equal to zeta omega n, so you can find the rest. Okay, once you know all of these values, the zeta, omega n, omega d, beta, and everything, you again can estimate the features of the step response: the rise time, peak time, maximum overshoot, settling time, using all of the formulas that we have already discussed before. And then by knowing all of these features, the rise time, peak time, maximum overshoot, and settling time, you should be able to sketch the step response. As you can see here on the right side is the sketch of the unit step response. As you can see here, the rise time is around 0.6. So this is the rise time. It's about 0.605. And this is the peak time, the instant when the response reach the maximum overshoot. This is 0.907 based on our calculation. The maximum overshoot is about 16% here, and the settling time is, with a 2% criterion, the settling time apparently is 2 seconds. So it seems that the window, the 2% window, is somewhere here, right? So this is the first time when the response reach and stay within this window at 2 seconds.